Okay, believe recording has started. This is lecture 5. Welcome to this one. This one's going to be a pretty important lecture because a lot of the questions on the midterm and the multiple choice from the final exam is going to stem from the concept of rectifiers. And rectifiers is a very, very important concept in electronics, one especially, because you learn a bunch of them. You learn about the half-wave rectifier, you learn about the full-wave rectifier, half-wave rectifier with one diode, full-wave rectifier with two diodes, and the center tap transformer. This will all make sense in the future. And as well, you learn something called the bridge rectifier. So there's a bunch of stuff right here that you're gonna have to learn regarding rectifiers. So this lecture is dedicated on the half-wave rectifier with one diode. But before I even proceed with the concept of rectifiers, I want to go through the rectification process. What does that even mean? So when you look at a plug, what you would plug or a wall plug in your house, usually in Canada, that's around 120 volts um, at a frequency of 60 hertz. So you have a sort of a sinusoidal signal, just like I'm drawing right now. This is the type of voltage that you have in your plugs at home. So these plugs, well, we want to convert that from an AC, all right, alternating voltage to a DC voltage. So this is what I drew here. We have a 120 volt RMS. RMS just means root mean square. Okay, so that's the RMS value. We have 120 volts RMS 60 hertz right here in your wall plug. So the rectifier is basically a big box. There's multiple processes that goes through before you actually go from AC to DC. The number one is a transformer. Now, your laptop does not need a lot of voltage. However, the wall plug is giving you 120 volts RMS. So that's like your amplitude. So you don't really want that high of a voltage. So you're going to use a transformer to bring that voltage down. After you've done so, the voltage has been decreased. It's still sinusoidal. You're going to have a rectifier circuit with diodes, right? And then associated with a rectifier circuit is a filter, usually a capacitor. And that will all make sense in a second. And the moment you have a capacitor, well, you can have your voltage shrink down even lower and change the shape of that voltage. It's not going to be sinusoidal anymore. And then the last part is what was on the previous lecture, xenodiodes. You're going to use the xenodiode to actually make that voltage as flat as possible, hence very close or ideally a DC voltage. So essentially the rectification process goes from a sinusoidal voltage just like that to a DC voltage like that. So we're going to start with the filter component and half-wave rectifier with an ideal diode. So we're going to go through this piece by piece so you understand every single thing right here. If you are able to understand this and you understand the process and the concept behind the rectification and the filter process, well, all of the rectifiers, it's only the circuit that's different. The steps to solve problems and the thought process behind everything, all of that remains the same. So here we have a one diode rectifier. So let me zoom on that circuit a little bit. So we have an input voltage going on here. That's and then we got a diode going on here. So that means that the current would want to flow in this direction. That's hence the direction of the diode. We have a resistor, and then we have a capacitor. And across from that capacitor is our output voltage. Now, one thing to keep in mind is the voltage across the capacitor right here is the same as the voltage across this resistor right now. Why? Because these two circuit components are in parallel, hence the same voltage. Now, one thing I want you to keep in mind is when time equals zero, okay, when time equals zero, as I press my stopwatch, time equals zero, my output voltage is equal to zero. Now, why is that? Because if you look over here, the blue curve is my input voltage, the red curve is my output voltage. So right now I've got a lot of stuff going on here. All I want you to focus on is on the laser curve right now. The laser curve that I'm drawing, that's my input voltage. Well, at time equals zero, right? At time equals zero, well, this point is 0 volts, right? My input is 0 volts. So if I come over here, well, this diode is going to be a short circuit, which means that my input voltage is going to be equal to my output voltage because this is a short circuit, this is a short circuit, right? And then these two elements are in parallel, hence the voltage are going to be equal, all right? This voltage is going to be the same as this voltage. And since this voltage at time equals zero is zero, hence the output voltage of the capacitor is going to be zero as well. And during these questions, we're going to assume that this value RC, so the value of the resistance multiplied by the capacitance, is much, much bigger than T, where T is the period of your sinusoidal function. So this is your sinusoidal function right here, and this is your value T, is the period, all right? Or you can say from peak to peak, this value right here, that's your period. It's the same thing. Okay. So during 0 less than equal to t, or I should rephrase this. When you have t, your time is between 0 and the period over 4. So we're talking about this range right here. If you look at my laser, we're talking about this range. Our output voltage is equal to the input voltage. Now, one thing to keep in mind is that at the start, when time equals 0, the capacitor is essentially an element that stores energy in its magnetic field. So when time equals 0, that input voltage is going to start to increase. So what's going to start to happen to the capacitor? It's going to start to accumulate energy in its electric field. It's going to start to charge, right? Because if you think about it in circuit theory, whenever we have had to replace a capacitor with another circuit element to do analysis, it's been a voltage source, right? Like a battery. So that capacitor, as soon as my input starts to increase, my capacitor is going to start to charge, right? It's going to start to accumulate energy in its electric field. So during that interval, if you look at the graph, during that interval, my capacitor is well charging, okay? So, but now that output voltage in red is the same as my input voltage during that interval because my capacitor is charging. Now, what happens if you look at the blue curve, right? The blue curve starts to drop very fast. Now, this blue curve, what is it? That's my input voltage. Okay, that's my input voltage. So my capacitor is charged to the peak value, right? If you look at this curve has a peak value called V peak. This is called the peak voltage. My capacitor has been charged to the peak voltage. So the capacitor, if you look at my hands, the capacitor is a high voltage VP. And then my input voltage starts to drop. So my output voltage is greater than my input voltage because the capacitor is fully charged and the input starts to drop. So what's going to happen to that diode, right? For the diode to work in in the forward region, right? I need this voltage to be higher than this one, right? But as soon as the input voltage starts to drop, well, the capacitor is at the peak value. So what's going to happen is the roles going to be reversed. The output voltage is going to be greater than the input voltage. So that diode is going to go from a short circuit to an open circuit. All right? So it's very important you understand that. Okay? I'll repeat it one more time, being more concise. As my input voltage goes from time equals 0, it goes and it reaches a peak value. Because the diode is a short circuit, the output voltage is going to be equal to the input voltage. When the capacitor has been fully charged, it's reached a peak value VP. It's very high. It's totally charged up. And as soon as my input voltage starts to drop because it's sinusoidal, at one point, the capacitor is going to have a stronger, higher voltage than my input voltage. So the diode is not going to be in the forward region anymore because of the voltage configuration, right? The output is bigger than the input, so it's going to be off. It's going to be a short circuit. So a circuit is going to transform to this. So now I have during t greater than t over 4. So this is t over 4. So during t greater than t over 4, so I'm talking about this kind of region right here. V0 would be Vp times E to the minus t over RC. Now, where does this come from? This comes from circuit theory 1. Because how a capacitor is going to dissipate its voltage is an exponential drop, right? That's the way a capacitor dissipates its voltage into the circuit because it's been charged. And then when there's no voltage source in the circuit, well, that capacitor is going to act as a battery. And the way it's going to dissipate that voltage will be sinusoidal. My bad. It's going to be exponential. So one sec. That's just from circuit theory. Okay. What did I write right here? Capacitor is fully loaded. V0 would be temporarily greater than Vi since Vi starts to drop. So that's just what I just said, right? What I just explained. Okay. So what would happen is that before, when we were in this region and this was on, right? So current, all right, current was flowing in this direction, right? Okay, it was this voltage was increased due to the increase in the input voltage. When the output is bigger than the input voltage, well, this diode is off, so we're in this case. So what's going to happen is this capacitor is going to start dissipating its voltage and it's going to start feeding current into that resistor exponentially. So when the capacitor dissipates its voltage exponentially, well, instead, if you look at the charging here, so the capacitor has charged, reached its peak value, the input starts to drop pretty quick, so the diode is not on anymore. So the capacitor starts dropping exponentially, right? It starts dropping exponentially until it hits this point. Now, what is this point? While the capacitor was dropping exponentially, the input voltage was still going sinusoidal. And then they reach this point where they meet. All right. So the capacitor has discharged, and now the input voltage is increasing. And now, because the input voltage is increasing and the capacitor voltage has already dropped, the input voltage is greater than the output voltage. So that means the diode is going to start conducting current again. And what happens when the diode starts conducting current? Well, the capacitor is going to charge and it's going to keep on charging. And then what's going to happen is that the input is going to start to drop fast again. Once the input drops fast, the capacitor starts to dissipate exponentially, and so on and so forth. So what happens to the capacitor voltage is it's just going to do this kind of pattern right here. Okay? So that's the main concept behind it. So now if you look at this graph right now, I just wrote that exponential decrease due to the capacitor right here. So we have this sort of situation going on here. Now this voltage difference right here, we're going to call it the ripple voltage, right? Why are we going to call it a ripple? Because these are like ripples, right? It's like ripples. So we're going to call that the ripple voltage. And it's very important for us to be able to calculate what a ripple voltage is. One more thing here. At this point, I said that the diode starts to conduct again since the capacitor starts to get charged, okay? So at that point, it's basically the same thing of what was going on right here, okay? So now what we're going to do is we're going to calculate the ripple voltage and the delta T. Now, one thing I want you to kind of pay attention to what I'm saying here is this is a derivation. And I think it's a very, very important derivation for this question because it might show up on a final exam or a midterm, especially a midterm. So I would say to understand derivation first, understand it one time and then memorize it. Okay? Because once you understand it and you memorize it, it's game over. You understand everything. Okay? So we need to calculate V ripple and delta T. What is delta T? So this is my ripple voltage, right? This is my ripple voltage. Now, if you look at this part right here where the capacitor is charging, well, again, from it just finished discharging, so it's charging again here. So this delta T right here, that's the amount of time it's going to take for it to charge again. So we want to compute this amount of time. This delta T, we want to calculate its value, okay? And at the same time, we want to calculate the ripple voltage value. So this is what we're going to do. So now we're going to say that V0, our output voltage, is equal to some Vk at T equals T minus delta T. So let's go back to the graph. All right. So this is a peak and this is a peak. So this is a period T, right? And if I take that T, I minus some delta T to it, I get this point, right? So this is T minus delta T, I come to this point. This point, if I extrapolate here, I'm going to call it Vk. Now, what is Vk? Vk is the output voltage at T minus delta T. So when the time is equal T minus delta T, V output equals Vk. If you didn't understand that, just rewind the video a little bit and I'm sure you're going to get it. So we're going to call that voltage Vk, okay? So that voltage Vk plus the ripple voltage is going to amount to the peak voltage. That's something to keep in mind. So let's go back here. So now we know that the capacitor voltage as a function of time is exponential, right? It's an exponential decay. So the voltage, the output voltage at T minus delta T, well, we just said that this is equal to Vk. So we're going to say that this thing is equal to Vk, which is equal to Vp E. The only thing I got to change is this T. This T is going to be whatever value I got here. So I'll plug that into my equation. And now, if I look at my graph, here, delta T is visibly much, much smaller than T. So that's my first assumption. All right. Delta T much, much smaller than T. So this delta T is going to disappear in my equation. And my equation for Vk remains as this. Now, at the start of the problem, I said that we're going to assume that RC is greater than, much greater than the period. And this is an assumption that you can make for almost all, like, I think, pretty sure, all rectifier questions. And because of that assumption, you can say that you can use a Taylor series approximation. E to the x is equal to 1 plus x. All right? That's just a Taylor series approximation. In our case, we don't have e to the x, we have e to the minus t over RC. So I can say that x is equal to minus t over RC. All right? So now the only thing that's left is that this exponential, instead of writing it as e to the minus t over RC, I'm going to approximate it. I'm going to write it as 1 plus x, where x is this thing. So I'm going to have 1 minus t over RC. So my equation is finally this, my equation for Vk. And let me just remind you that Vk is the voltage right here, okay? Now, why did we bother going from an exponential to a function like this? Why did we approximate it? Well, that's because it's much easier to work with a linear function right here than it is with an exponential function, right? So we're kind of saying that, oh, this is the deal. We're gonna approximate our equation, make it linear so we can understand more, do less math, and it's still pretty accurate. That's the whole point of it. So we're here right now. Now, if you remember correctly, I said earlier that Vk plus the ripple voltage is going to amount to the peak voltage, right? The addition of the ripple plus the Vk that we define is the peak voltage. So I can write it here. V peak is Vr plus Vk, okay? Now, what is Vk? Vk is whatever I got going on here. So I'll take it here and I'll replace it for Vk. So now I'm just going to take this Vp and distribute it inside the parentheses. I'm left with this equation, right? When after I bring my Vp inside the equation right here. So I have this thing equal to this thing. And that's what I wrote right here. Okay, that's what I wrote. So I have Vp equals to Vr plus Vp minus Vp times T over Rc. I have Vp on both sides of the equation so I can cancel them out where I get this thing. Now all I got to do is isolate for Vr and I get this equation, which is the ripple voltage equation. So it says that V ripple is Vp, which is my peak voltage, times the period over Rc. Now I know that the period is 1 over the frequency, so I can replace T by 1 over F, and the equation simplifies to this. Both of these equations really just mean the same thing, okay? So that's the equation for my ripple voltage. So again, understand the derivation, pause the video, go through it yourself, make sure you understand it one time, and then practice it over and over, memorize it so that when you're given on an exam, you can just get through it and then you understand everything and you get it right. So now we just calculated a ripple voltage. However, we said that we also want to calculate the delta T. Now, as a reminder, the delta T is the small time it takes for this capacitor to charge itself again in that small time interval. So computing delta T. Now, we said that delta t is much smaller than t, okay? So if I go back to my graph here, this is much smaller than t, so we can assume that this thing is as small as possible, right? We can assume for it to be a point. So stop thinking about delta t as an interval, like a small gap like this. I want you to think of it as a point. Imagine this line, and I push on both sides, and I want to make it like a single line, all right? So we're just going to compress our delta t into one singular point. And if we do that, and we know that delta t is much smaller than t, and we do that, we just compress it into a singular point, we can basically say that at that singular point, our vk is a sinusoidal function. So let's go back here. So delta t is going to be this point right here, okay? Or any, just like, never mind, actually just this point, because this is my vk. So this point is delta t that I'm highlighting right now. This is my delta t. And if you see, this point that I just highlighted is on the sinusoidal graph. So if delta t is my point, at t equals delta t, at this point right now, my vk follows the sinusoidal function, all right? Okay, let's go back here. So we have vk equal vp cos omega t. There we go. So because delta t is very small, we're going to use a Taylor series approximation. cosine x is approximately equal to 1 minus x squared over 2. In our case, x is omega delta t. So we have Vk equal Vp cos omega delta t. Now again, cos of whatever the hell is going on in here is equal to this thing, okay? Especially with our x being omega delta t. So I'll just replace this cosine with my approximation right here. That's all I did. Now from here, I have Vk equal to this thing. Again, V peak is Vk plus Vr, right? The summation of Vk and the ripple voltage gives you your peak voltage. But in this case, I want to replace Vk that I got here with Vp and Vr. So I'll isolate for Vk, and I get that Vk is Vp minus Vr, and I'll take that and I'll plug it in for Vk. So my expression comes right here. Now all I do is I distribute this Vp into the brackets here, and I have Vp minus Vp times this thing. Okay, so Vp minus Vr is equal to this thing that's going on here. So that's what I wrote right here to clean things up. So now I'll bring all the VPs to one side and all the VRs to the other side. So VP on this side, VP on this side, these two are going to cancel out, just like I did here. And we have 0 equals VR minus VP times omega delta t squared over 2. This is just math, guys. This is just math. Okay, it's all about knowing the process. This is just algebra. Pause the video, go through the algebra yourself. You get confused, you can follow the steps and you get there. It's not that hard. Okay, so we have this thing going on here. So VR, I just need to isolate for the ripple voltage here. VR is Vp times omega delta t squared over 2. Now remember, our goal is to find delta t. So all I gotta do is isolate for this delta t. So we got this equation right here. Okay, I'll take the square root on both sides. We get to here. I divide by omega on both sides, and this is my equation for delta t. Nice and simple. We find that the equation for delta t depends on the ratio of the ripple voltage and the peak voltage times 2. You take the square root and you multiply that by 1 over the angular frequency. So this is my equation for delta t. And now, if you go up a little bit, I said that this was an ideal diode in the sense that this diode, when it's on, is just a short circuit, and when it's off, it's going to be an open circuit. But now, what if things are not so ideal? If things are not so ideal, the concept remains the same, but you have to remember, so look at my graph right now. Look at my tablet. So I've got on my screen, I've got a diode. So this diode, if it's ideal and if it's on, is going to be a short circuit, just like that. However, if this diode is non-ideal, it would be something like this. We have a diode in series with a voltage source and a resistor RD. This is going to be VDO. However, this RD is very, very small, so we can basically assume for it to be a short circuit. Okay, that's a classic assumption in this class. You can always do that. So basically, my diode model is going to amount to this. So we have diode here and VDO right here. That's going to be my model. In this case here, it was just a short circuit. We didn't have any VDO, okay? But if it's non-ideal, we have a VDO we need to account for. So look over here. Non-ideal diode with a filter component, RD diode resistance can be ignored. So basically what I did here is I replaced my diode with a non-ideal model. So I have VDO here. Now if you do a KVL right here, okay, I'm going to have that minus VI plus VDO equals V output, right? So what do I got going on here? So if I wanna, I'm gonna have that VDO equals V output plus V input. Okay, so V output is VDO minus V input. Okay, so these are the equations I can write from that KVL. And of course, I'm just assuming that this diode is a short circuit when I'm writing these equations. So when V input, so this voltage, is greater than V0 plus VDO. V0 is my output here. Okay, so when this part, the input is greater than this, right? When this part is greater than this part, this is the negative side of the diode, this is the positive side. So this diode is essentially going to be on. So that's case number 1. I said we had two cases. When VI is greater than V0 plus VDO, so this voltage, where the plus sign is greater than this voltage, which is the sum of this one and this one, right? This diode is going to be on. And the second case, when VI, when this is smaller, so the positive side is smaller than this, oh, sorry. When the positive side is smaller than this side, right, then the diode's going to be off. And the reason why it's on and off is because of the of reasons we've talked in the previous lectures. So if you're a little bit confused about that, I would recommend you go back, watch the previous lectures, and then come back to this one, and it will all make sense. Okay, so VDO is V input minus V output. All right. So VDO plus V output is V input. So I can write that my V output is V input minus VDO. Okay, that's just simple algebra. Okay. So my output voltage is my input voltage minus my VDO. So what we got going on here is that when this voltage V input starts to increase, so I want you to focus on the blue curve again, okay? Let's say this input voltage starts to increase, right? When the input voltage at t equals 0 starts to increase, my output voltage, the capacitor got no charge inside of it, so it didn't store anything yet, right? At t equals 0, it doesn't have any charge inside of it. It didn't store any energy, so its voltage is 0. And this diode is not going to turn on straight away. Why? Because my input has to be higher than VDO for this diode to turn on, right? Because if you look over here, this value is going to be VDO, right? So this input voltage right here has to be greater than VDO for the diode to start conducting because this is non-ideal. So the voltage of the diode, oh, no, actually, never mind, the voltage of the input is going to keep on increasing. And then when it passes VDO, right? The capacitor, there's no voltage going on in the capacitor. The capacitor is not going to be charging, right? Why is it not going to be charging? Because the input did not pass VDO yet. And what happens if the input did not pass VDO? This diode is not conducting yet. So no current, right? No current is flowing through that resistor, and the voltage in that capacitor is not increasing. Okay? So if I zoom in closer, the input is increasing. It did not hit VDO yet. So the diode did not start to conduct. If the diode didn't start to conduct, that means there's no current in the resistor. No current in the resistor means the voltage and capacity did not start to increase yet. So this is the voltage and capacity, right? The red line. So it's still 0. Now when the input hits VDO, right, the diode starts to conduct. So current starts to flow into that resistor. So what's going to happen is the voltage inside the capacitor is going to start to increase. And then as the input increases, right, the capacitor keeps on charging. However, the input can only go so much, right? So the capacitor gonna stop at some point, but it's never gonna be at that peak voltage, right? There's gonna be a difference, and that difference is equal to VDO, right? That's the only difference. So it's going to take a while to start charging because the diode is not conducting. The voltage of a capacitor increases, decreases exponentially due to that exponential decay, and then it increases again, and then decreases, increases again, and then decreases. All right, let me get a sip of my tea, and then we keep on going. So as I've said before, is that this capacitor voltage, right, it's never going to peak to VP again, right? Because there's a difference of VDO, right? VP minus VDO is going to be the new peak of the capacitor. So this was usually VP before. However, due to the reasons we just talked about, this peak voltage is going to be VP minus VDO. So this is going to be the first difference in our equation. And the procedure to derive the the procedure to derive the ripple voltage is the same, except this is non-VP. We have to account for the VDO drop, and so that's the only difference in our equations. Excuse me. So I hope you understood a lot from this lecture because I really went through the concepts and a little bit of the derivation that I thought was important. I think if you look at your lecture notes with your professor, you're gonna have some equations about the ID max, IC average, and stuff like that. Go through them, go through the notes, try to understand these things. But I wouldn't pay a lot of attention in that because they're very like niche things that, in my opinion, does not deserve a lot of time and attention. I think the ripple voltage is something you need to memorize. These current derivations are way too complex for someone to memorize. It does not make sense to memorize them. But definitely go through them, understand them, see what they mean, and everything like that. I won't be going through them because I don't think it's important, but still, you should go through them and try to understand them. And in future videos, we're going to talk about the full wave rectifier with the center tap transformer, okay? And maybe the bridge rectifier as well. We'll see if I can get through that because my goal with these rectifiers is to just give you the basic concept. The moment you understand the simplest form of rectifier, you can apply that knowledge to the more complex forms of rectifiers, right? And it's going to be good practice
for you to go through these mathematical equations by yourself. So make sure you understood everything that went on in this lecture. Go back, review it multiple times, and try to derive everything by yourself. And with that being said, we'll look forward to the next lecture, and hope you guys are enjoying the videos. Also, though, I saw a couple of comments. These comments mean a lot to me. Okay, I really love seeing these comments. If you guys want to put a comment there, you're just going to make me even happier. And I try to keep these videos for coming as long as I can, and as long as I can push myself through. Actually, record them, sit down, write my notes, and then post them. So it's been fun doing that. And the only way I can feel some sort of fulfillment doing these things is receiving feedback from you all. So the guys putting in comments, the guys replying back in the IEEE Discord server, I really appreciate you guys. And if you want to see more content from an unconventional small YouTuber, hit that like and subscribe button, and until next time.